predicted 30 solar mass binary black hole at GWPAW 2015. This stands for Gravitational Wave Physics and Astronomy Workshop 2015 at Osaka in Japan. Because the black hole mass of GW15914 is about a factor 2 to 3 larger than that of the black hole candidate X-ray stars. Most of the X-ray candidates is at most 15 solar mass. And there is a slide by the summary talk of GWPAW 2015, June, by Bruce Allen. And he said 30 solar mass black hole is interesting target for 3 reasons. One is that in-spiral and ring-down phase have roughly equal SNRs, so provides a good test of GR. This is the equal mass case mass, and this is the detectable range of the chirp signal. This is the detectable range of the quasi-normal mode, QNM. So this is a very good point. And second point is that if population 3 stars formed at redshift 5 to 10 exist, these might be a substantial fraction. And finally, perhaps we will detect several of them in the first advanced LIGO data run 01 this September. Remember, this conference was held in June. So next year, this slide was shown in GWPAW 2016 in Boston, first by the organizer saying, we predicted the GW15940 beforehand. And my summary talk at the GW 2016, one of the slides is that why GW15914 was detected first. Probably because as for the chirp mass, binary black hole is larger than neutron star black hole, and neutron star black hole is larger than neutron star. And the detectable range is proportional to 5/6 power of the chirp mass, and the volume is 5/2. So that naively, black hole BBH is the easiest detectable source from this argument. So assuming that tendency, I predict the neutron star black hole will be observed. However, in reality, my prediction was not the case, and neutron star merger was found. Now, first I want to argue the quasi-normal mode, or QNM in short, and the confirmation of the Einstein theory in the strong gravity region. And there is a uniqueness theorem of the Kerr metric by Israel Carter Robinson exists. This is called the no-hair theorem or cosmic censorship usually. And first we assume Einstein theory is correct. And second, we assume no singularity exists outside the event horizon. Then it is proved that the Kerr metric is a unique vacuum solution of the axially symmetric stationary asymptotically flat space-time. The essence of the proof is as follows. Assume that the 2 solutions with same mass and angular momentum exist. Then using the Einstein equation in vacuum and Robinson's identity, you can prove 2 solutions should be the same. And Kerr metric satisfied this condition too. No singularity exists outside the event horizon, so that it is a unique solution. However, there are many asymptotically flat axially symmetric stationary vacuum solutions of Einstein equations. For example, Toyama-Sato solutions are such an example. And the Toyama-Sato solutions are characterized by the parameter delta. And for delta equal 1, the solutions agree with the Kerr black hole. And this is the cylindrical, and you show the reflection. We assume the reflection symmetry. This is the rotation axis. And this is the event horizon. And the singularity is inside the event horizon. However, for delta equal 2 case, event horizon is here, and the singularity is outside. And the delta equal 3 case is also, there is a naked singularity. We call this naked singularity. Singularity outside the event horizon. The problem is naked singularity can be observed so that the violation of physics propagates to us. This is a very dangerous situation, so that it should be prohibited. But how about the unfortunate person? Even in the Kerr metric, the singularity exists inside the event horizon. However, it cannot be seen by the observer outside the event horizon, so that we are safe. So let's consider the unfortunate person who is dropping into the Kerr black hole. Does he or she is killed due to the strong tidal force of a black hole at the event horizon? If he or she is killed, she cannot feel what is happening inside the event horizon of the Kerr black hole. However, let's consider a black hole of mass 10 to 8 solar mass in the center of a galaxy. There are many examples of this kind of a galaxy. And in this case, the size of the black hole is 1 AU, very big, so that the tidal force between her head and the front is only 10 to minus 6 g, where g is acceleration on the surface of the Earth. So she will be safe at the horizon. Even for 10 to 6 solar mass black hole, like in our center of galaxy, tidal force is almost g. Then she will feel the effect of the singularity and may not be safe in the classical theory. In any case, the infinity, here the infinity is the curvature invariant becomes infinity, is not allowed. Infinity is not allowed in physics. So Einstein gravity does not include Planck constant, so that the quantum theory of gravity will turn the singularity to be safe. I believe so. If so, the naked singularity in Tomimatsu-Sato-like metric might also become the harmless one. This means that we might see Tomimatsu-Sato-like metric modified by the quantum gravity in the real black hole motion event like GW15914. I think the situation might be similar to a hydrogen atom in the classical theory of physics. In the classical theory, the electron in the hydrogen atom is accelerated and emits electromagnetic wave to fall into the central proton so that the hydrogen atom cannot exist. However, as we know, in quantum mechanics, hydrogen atom exists. The singularity of black hole might be similar to the hydrogen atom in the classical theory. One might say that the effect of quantum gravity is limited to the Planck length, 10 to minus 33 centimeters, so that essentially the structure of naked singularity may be similar to that of the Einstein gravity. However, there is an example that microscopic physics affects the macroscopic phenomena. Example is the radiation pressure is a macroscopic quantity with pressure is 1/3 times T to 4. As we know, Planck constant is needed to calculate the radiation density constant A. So as I show later, Qn, quasi-normal mode, is emitted from the space-time near the event horizon. Then, from the above line of argument, the effect of quantum gravity might be seen in the behavior of quantum QNM of black hole. If QNM is different from the expected one from the Einstein theory. Therefore, QNM is very important to confirm or refute the Einstein theory of gravity. So, this is a figure as Ray already showed. And for this GW15914, Kerr parameter A/m is around 0.6 to 0.72. And you can see QNM-like oscillations here. This is the numerical relativity calculations. And QNM looks like this for larger signal-to-noise ratio. And it carries the information of strong gravity. And this QNM depends on the Kerr parameter A/m. And this is the numerical calculation of a gravitational wave emitted by a small particle with zero angular momentum falling into Kerr black hole in the equatorial plane. And this dotted line is A equals 0 case. And this is the retarded time. This is the amplitude. Nu is the mass of the small particle. R is the distance from the center of black hole. And for A equals 0.99, the QNM lasts very long. So QNM is a complex frequency which does not depend on how it is excited. It reflects the space-time of black hole. But how? There is a fitting formula of the results of numerical calculation of QNM for LA equal M equal 2 and least damped mode. And this is the real part of the QNM, FR. The FR is the imaginary part, but we use a quality parameter, Q parameter. Then empirically, the frequency is written, QNM frequency written like this, and Q parameter is like this. Here, alpha M is remnant mass over M remnant parameter. And if we plot this in this figure, this is the frequency. This is the imaginary part of frequency. And for 30 solar mass cases, this is the A equals 0 case. That is a Schwarzschild. And then 0.2, 0.3, and 0.9 up to. And for different mass, the QNM behaves like this. And this is 60 mass solar mass case. And around here corresponds to DW15914. And you can see there is a prohibited region in general relativity. So if QNM is found in the prohibited region, it contradicts Einstein gravity. And these papers, they showed in fact case we can determine QNM and say Einstein theory is correct or not. So we are asking what amount of signal to noise ratio is needed. And this is the fitting formula of numerical relativity of the merger of M1 and M2 black hole with 0 spin. Then that for equal mass case, the remnant mass becomes 0.95 of the initial total mass, and alpha parameter is alpha equal A over M parameter, K parameter is 0.68. And we calculated if SNR is 35, then the 5 sigma region becomes like this. So probably for SNR 35 for QNM seems to be large enough to say QNM for Einstein theory. So what is the origin of QNM? And in Schwarzschild case, the metric here, and metric perturbation is described by either Legge-Wheeler or the Rayleigh equations. And this type. And this looks like quantum mechanics, or potential problem in quantum mechanics. And Schutz and Will in 1985 showed that the peak value of the potential and the curvature there determine QNM by WKB approximation. And the formula is like this. And this is how they derive the equation. So it looks like the equation looks like the potential problem of quantum mechanics, and they assume the parabolic shape inside this central region, and fitting two formula, two wave, and putting outgoing wave here purely ingoing. This side is the event horizon, and this is the outer infinity, and purely outgoing. So you have some eigenvalue problem, and they solve that approximately. And for Legge-Wheeler potential curve like this. So the peak is around 3.28, and they show that second derivative is it determines the imaginary part. So essentially, the space-time around R equals 3.8 from the peak, and the curvature from the second derivative. Curvature there determines. So the space-time around R equals 3 can be identified, can be confirmed by observing QNM with SNR 35 or more. And in reality, how is the accuracy of this approximation? This is L equal 2, 3, 4, the usual L in quantum mechanics, tensor spherical harmonics, L. And this is a numerical one. This is WKB one. And accuracy is 7%, 1.6. And the imaginary part, this is important, but accuracy is rather good. So we adopt their formalism, and we extend the method to Kerr case. In case of the Kerr metric, while tensor perturbation equation is separable and called as Chukovsky equation, however, Chukovsky equation has a long-range potential and divergent source terms in general. This is a Kerr metric, and the Chukovsky equation is here, and the various definition of the quantity here. And the source term diverges as in proportion to 7/2 for particle falling into the Kerr black hole. And the potential V takes the long-range nature. And in 1982, we proposed the following transformation of the Chukovsky equation, and to have a short-range potential and convergent term. There are many solutions, but anyway, this is a new equation. And putting a variable to change like this, then the form of the equation becomes like this. This is essentially similar to the Regge-Wheeler equations. And the Regge-Wheeler equation, in reality, get back for A equals 0 limit. And potential is written like this. And we apply the Schutz and Will treatment to Kerr case using this potential. And complex frequency will be given by. And the result is like this. This is the A over M parameter. This is the R parameter. And this curve is the value at the maximum of VSN, the Kerr version Regge-Wheeler equations. And for GW15914, A over M is estimated around 0.7, so that the space-time around 2M is 0.7. 2M is responsible to quasi-normal mode. And the accuracy of the real part and the imaginary part is here. And this dotted, this circle shows the WKB method. And this solid line, red and blue, shows the real numerical solutions. And you see that the difference is not so large. And this is a diagram of the error, and below 10% or something like that. So in case of this black hole, there is a possibility we can confirm the space-time around 2M by QNM. So Schutz and Will's method seems to work well even for Kerr metric. And the Twyla proposed different transformation defined by these equations. And anyway, finally, they get the similar equations. He gets got a similar equation like Regge-Wheeler equations. And in this case, the up to 0.95 Kerr parameter, this Q is Kerr parameter. You can do a similar thing. And this is the solutions of the peak radius. And this is event horizon. And this is the accuracy of the imaginary part and the real part. And this is the error in percent. So the below 2%. And transformation discussed by our by us has two arbitrary functions, g and h, which should be constant for r equal infinity. And these are formulas. Anyway, we change the g. This is some arbitrary function. Then we get a very smooth peak, even for Q parameter. A over M is 0.99999999999. And solution becomes like this. The peak is this blue line, and with black dot. And this red line is the radius event horizon. So up to the very close to the extreme curve, the Schutz and Wheels method seems to work well. And this is the error. Anyway, in this case, R peak approaches horizon radius for the extreme limit. Therefore, we could say that the QNM with small imaginary part will confirm the space-time near the event horizon region if it obeys that of curve metric. If not, Einstein gravity might be refuted there, or some information of the quantum gravity is needed. So there is a problem. So how to distinguish QNM from merging phase? This is a numerical solution. This looks like QNM, but how about here? How about here? How about here? And O'Hara's group found some good method to separate ring down phase and merging phase. This is a numerical. They use a numerical solution, numerical relativity solutions, and this green line shows the instantaneous frequency. And they are using Hilbert-Fan transformation. And from here, it looks like the frequency is constant. So we may say from here, QNM starts. Their transformation is like this. Suppose this is a signal. Then they divided this wave pattern using this kind of, not a Fourier transform, but this kind of a unique sum. And all these functions are analytic, so in the local time, you can define the frequency. Anyway, now, I would argue origin of the GW15914 like BBH. Mass range of 5 black hole events in 1.5 sigma from Live and Bargo papers. This is a minimum mass. This is high mass and low, high, and so on. And 3 black hole BBH have final mass greater than 44 solar mass. At least, I think, 4 origin of BBH with 5 to 41 solar mass. One is a primordial black hole formed from the perturbation in the radiation dominant R universe. And population 3 stars, the first stars after the Big Bang with no metals, no mass loss. These stars should exist, but they have not been observed. And population 2 stars with 0.1 to 0.01% metal, and population 1 stars like our sun. I think many papers appeared in the archive and with many good ideas to distinguish each model from other models. To review all models is beyond my scope at present, so that I will discuss only 3 topics. Why 30 solar mass in population 3 model case, as Bruce cited. And next, when and how primordial black hole was noticed as a source of gravitational wave. This is related to the detection of a gravitational wave in Japan. And third is a possible smoking gun to distinguish models. First one, why 30 solar mass in population 3 model? This is the HR diagram of the population 3 stars. There is a strange behavior. For 30 solar mass, below 30 solar mass, the evolution ends almost this blue squares. But for higher solar mass, the evolution ends here, and higher mass becomes a red giant. But smaller mass ends its life as a blue giant. So while the larger mass star ends its life as red giant with large mass loss in the common envelope phase, so that in this case the mass is lost, and finally it becomes the 30 solar mass or something like that. So this is the reason. So the 30 solar mass comes from the HR diagram of population 3 stars. And this is the numerical simulation of the population census for population 3 stars. And this is the standard case, the flat IMF. This is the salpeter-like IM. And at present, 5 black hole comes around here. This graph is shown as a function of sharp mass, and this is the number of merging black hole in this mass region. And if you if you write the cumulative distribution function, for salpeter like this, and population standard model flat IMF becomes like this. Of course, 5 BBH is not into something, but if the number of BBH increases, fit of the cumulative distribution function is important. And moreover, that population star formation rate has a peak at around z equals 10. This is the model of the Dussault et al. And there is a formation at the z equals 30 to the peak at z equals 10 and down. When and how primordial black hole was noticed as the source of gravitational wave? I think this paper is probably the first one. And we wrote a paper with Gibson, and we started and completed this paper when we were in Japan. At that time, we had Japan-US cooperation of the research of the gravitational waves. And it is written, the coalescence rate will be 5 times 10 to minus events per year per galaxy. This suggests that we can expect a few events per year with even 15 megaparsec up to Virgo clusters. And the gravitational wave from such a coalescent black hole macho binaries can be detected by the first generation of the interferometer. And around 1994, using micro-lensing observations, it was said that dark matter might consist of macho, massive compact halo object with mass about 0.5 solar mass. The story is like this. Here is our galaxy, and here is LMC. And people observe 10 to 6 stars in LMC every day. And the macho, massive compact halo object, we don't know what is macho. But anyway, this is dark. And if this passes through the line of sight, then due to the gravitational lensing, a star becomes bright like this. And the important point is this increase of the magnitude does not depend on the color of the electromagnetic wave. And this is a very good example. And this duration is about 30 days or so. And from this duration of the flare-up, the mass of the lens is estimated to be about 0.5 solar mass. So it was claimed that the macho can be all the dark matter. Around 2025 in Japan, there was a top-down proposal to make 300-meter laser interferometer at the National Astronomical Observatory. I was against this proposal since no gravitational waves can be detected by such a small interferometer, and asked experimentalists to reject the top-down project. However, they finally agreed the proposal and started the construction. Their strategy was, if there is a good gravitational wave source which can be detected by Tama 300, we might detect the gravitational wave directly first in the world. Then I was asked to find or make the good source of the gravitational wave which can be detected by Tama 300. Tama 300, this is a 300-meter antenna, half underground. And the inside is like this. And finally, they wrote a paper in 2001, stable operation of a 300-meter laser interferometer with sufficient sensitivity to detect the gravitational wave bands within our galaxy. And their record of the continuous running is 2,000 hours or something like that. Then we tried to make G-wave source which can be detected by Tama 300 with KIP, I think. And I got this idea on my way in the airplane to go to Caltech. And let's assume that matter is a black hole. Then it cannot be formed from the usual gas since 0.5 solar mass star is sustained by the degenerate pressure of electrons. The only place in the universe where such a small mass black hole can be formed is the radiation dominant early universe with temperature 1 GeV. Then the Jeans length is almost the same as the cosmological horizon length CT with t equal 10 to minus 6 seconds. And to explain all the dark matter by such primordial black hole, it is enough that only 10 to minus 9 of the radiation turns out to be black hole. So let's assume that the PBH is formed randomly. Then the separation of a certain pair may be smaller than the mean separation. This region turns out to be matter dominant earlier than the radiation matter equality time. So the outside these two black holes, the universe is keeping a radiation dominant stage. Then two black holes, PBH, collide finally to be a larger primordial black hole. However, there should be the third black hole here. And tidal force by this third black hole will make two primary black holes as a binary, so that the margin time due to the emission of gravitational waves can be the age of the universe at present. This is 2, and the tidal force is larger here, smaller here, so the angular momentum is expected. And these are the arguments of the derivations. And we set the scale factor R equal 1 at matter radiation equality. And let x bar be the co-moving mean separation of PBH, and we consider the x smaller than x bar case, so that the nearer one be a certain pair of PBH. Then this local region becomes matter dominant universe for R larger than Rm. Rm is smaller than 1. So before the matter radiation equality universe as a whole, this means that the binary decouples from the expansion of the universe and becomes a bound system. Background universe is still radiation dominated. Then two PBH merge to a single PBH in the free fall time scale unless they get another momentum, angular momentum. However, the tidal force by the third PBH with co-moving distance y gives the angular momentum to the binary. Then the semi-major axis and minor axis of the binary is estimated as semi-major axis is x times Rm. And B can be estimated as the tidal force times the free fall time square. Then the B becomes like this, and you can get the eccentricity distribution, eccentricity as a function of x and y. And since x and y have uniform distribution with x smaller than y, y smaller than x bar, then we have the distribution of A and E as distribution in x and y is like this. And you can change the variable to semi-major axis and eccentricity. And the margin time due to the emission of gravitational waves is given by Peters and Matthews as this expression. Then we can convert this distribution function, the distribution function of the margin time. And the result is like this. So in the halo of a galaxy, black hole macho of mass 0.5 solar mass, then 10 to 12 BH machos exist. Then the event rate of margin primordial macho, primordial black hole macho is 0.01 events per year or something like that. So up to about cluster, a few per year. And expected gravitational amplitude is like this. So the probability that Tama 300 will detect the PBH binary is 5%, which is similar to the consumption tax at that time in Japan. Not so large, but not so small. Experimentalists were very glad since good motivation to Tama 300 construction was given. Later, observation of matter showed that the matter is at most 10% of dark matter. And now, mass of PBH is a free parameter in the above story, so that GW15940 can be PBH if mass is changed from 0.5 solar mass to 30 solar mass. This is a paper by Sasaki and others. And in this case, we know the value of the event rate. Then this is a fraction of the PBH. And this is the event rate. And just 0.01, 10 to minus 3 of the dark matter. If the 10 to minus 3 of the dark matter is PBH, that is enough to explain the GW15914-like event. So very recently, PBH can be, or the dark matter is possible or not, is now discussing. So there are many papers and discussion on this possibility. And this is a mass, this is a fraction of the PBH. And from Carr et al. Papers, there is many restrictions and so on. Third, possible smoking gun to determine the origin of GW15914-like PBH. What is a smoking gun to determine the origin of, or origins? Maybe two origins may exist. And there is a good example in the history of GRBs. Before 1997, the distance to GRBs were not known at all. Most people consider the halo of a gas 100 kiloparsec. There are only a few people, including Paczynski, proposed that the cosmological distance. But there was a smoking gun. This is the absorption line of GRB 17508. And this clearly shows that GRB is here. There is an absorbing cloud at Z equal 0.835 or 0.768 and so on. So this almost killed 2,000 papers. And the population 3 and population stars, for example, were formed mainly at Z equal 110 and Z equal 6 respectively. For primordial black hole, merger event occurs even at Z equal 35. This means that a smoking gun might be available by the observation of the peak or the highest redshift event of massive BBH merger by G-wave. And one possibility is the DeSigo. DeSigo project is that I have no time, so I will skip. DeSigo project is proposed DeSigo. This means 0.1 Hertz band detectors. Here is LISA, here is LIGO, and in between there is a vacant space of the band. And DeSigo is the detector like this. And very interestingly, 1 year before the merger of neutron star, the gravitational band is about 0.1 hertz. And we have a plan and so on. Now, we are considering the B decigo. B stands for basic or base or something like that. And we first make a triangle-shaped interferometer on the 2,000 kilometers on the Earth. And design of the cycle is like this. And where load map is like this. And the sensitivity of the B decigo is for BBH is like this at z equals 1. And the maximum achievable distance is like this. And this is the accuracy of this is the SNR and accuracy of angular directions and distance and time of the coalescence. And this shows the redshift as event rate as a function of redshift. This is a primordial BBH. So up more than, even if the redshift more than 35, there exists an event. And this is a population 3, and this is population 2. So I have no time, so I will finally show that angular resolution of gravitational antenna is using a time difference of the arrival. Then the angular resolution is determined by the distance of the two detectors divided by the wavelengths of the gravitational waves. For this latent, for 0.1 hertz case, this factor becomes 0.01. And for SNR 100, the angular size becomes 20 arcsec or something like that. Then for 1.1 solar mass case, in reality, using the Fisher matrix calculation, the direction determines below 1 arc minute. And the time is below 1.1 second, 0.1 second. And this is the time history of the prediction of the locations, margin location. So 1 day here, 1 week here. And for example, using this, we might observe the counterjet of off-axis width. And then we will get more data. Summary. Merger of GW15914 like BBH is the ideal black hole to observe QNM to confirm or refute Einstein theory in the strong gravity region. To confirm the origin of GW15914 like BBH, redshift dependence of merger rate is crucial. For this purpose, the construction of this cycle is interesting. The cycle can determine the time and the direction of the merger of neutrons and neutrons beforehand, so that we can prepare the various observations to know the important physical parameters of SGR and possibly FRB, like solar eclipse. Thank you for your attention.
Thank you. We don't have that much time, but perhaps there's an urgent question that somebody would like to ask and clarify. Mine's not working.
What is the funding status of this IGO?
Funding, not now. We are trying. We are now in a level of R&D level. And before 15/9/14, even in the starting stage, the ISAS request us some results. But after the GW15914, we can say that there is a possible target, certainly. So I hope the situation will change.